So in this session, we will introduce the basic equation in integral form for a control volume. We already defined together what is the definition of a control volume. And we said that we have difference between control volume and system. And I will remind you of this. So we have first, a control volume is a certain geometry, okay? It's a volume in space, and it is independent of the mass through which fluid may flow. Because for a control volume, the particles going through the control volume will be different. Yani, for example, if you consider the following engine and you have flow through the engine, at each instant, particles inside the engine will vary. So we have particles that are coming in and others that are going out. So we might have accumulation of mass. We might have, in case of steady state operation, we will have m dot inlet equal m dot outlet. So the rate of mass at the inlet will be equal to the rate of mass at the outlet. But we can have transient application where we can have accumulation here. Okay? So this is the boundary here for our control volume. For example, we can just consider, we can put any limit. So this is effective limit if you want. And then everything coming in, let's say you have fluxes coming in and fluxes coming out. While for the system, what is the main difference between a system and the control volume is that the system will always follow the same mass, okay, the same atoms of fluid particles. So if they move, we should move with them. So we should go with them to still have a system. So for example, we can consider, let's say, if you want, let's say we have a balloon, okay, but we have air inside, but this cannot connect with the environment. So you cannot have fluxes coming out or fluxes coming in, but you can compress air here, or you can, by changing its, by putting forces on it, you can increase its pressure. So, but the mass will remain the same. So we can explore what is happening with this mass with time, but this mass is not changing. It can change in volume, because if you have an ideal gas, let's say, you know that for the same mass, I can have different volume depending on the pressure conditions. So from here, just 1 minute, okay? I will be back with you, just 1 minute.
Bonjour, docteur.
Okay, so we were talking about the difference between the system and the control volume. So in general, the control volume can be a moving volume. This means that the surface can expand. For example, if you take a balloon and you are introducing air to it, okay, when you consider this is your boundary, this is a control volume because the mass is varying in this balloon. You can introduce air to it, and you can have gases that get outside. Okay, so as you introduce a gas in it, the mass will increase, and also you can have expansion of your volume due to this effect. So you will have a moving control surface, a control surface of with a certain velocity, because this boundary can expand with time. So a control volume can be a fixed control surface, as the case of jet engine example. So if you take the jet engine example, you have, this is a fixed control surface, and you have fluxes coming in and out. while for the balloon, the control surface can move. Okay, so we will consider different cases of fixed control volume and moving control volume. The same also for a mass. We can consider a fixed a mass of fixed surface. Also, it can be characterized by a certain motion. And we'll see in each case how to deal with it. Now, what are the different analysis approaches that are used in this case? We can use the Lagrangian approach or the Eulerian approach, and we already have seen also what can be the difference between these two. So I will give you again an example. If you have, let's say, a certain pipe, and you have particles that are coming in and out, okay, you can follow a particle as it moves and look at its path. If you follow the particle, then your interest is the particle itself. This is a Lagrangian approach, okay, because it will like if you have a bird that is moving, you are tracking its motion. So this is a Lagrangian approach. However, in the other case, if you just look at a certain part in the space, what is happening in this part in the space, if you have, let's say, if we take the same example, if we observe this part where we have particles that will come in and others that will go up. So both approach can give you an idea about what is happening, okay? But they are different. So because the Lagrangian approach will track the particles, while the Eulerian approach will just look at a fixed point in the space and see what is happening. And at the end, okay, both can give you good results. And we will see in this chapter that if you combine, if you can, you will come up with a theorem that will combine both approaches, which is called the Reynolds transport theorem. And this theorem is very important because it will be the basic for all conservation equations that we'll develop. We will develop equations for if you want continuity of mass, for linear momentum, for energy, conservation of energy. So all of these equations will be based on one theorem, which is called the Reynolds transport theorem, that we will derive together.
Bonjour, docteur, كيفك?
So as we said, we have
Hi,
a
doctor.
small problem that the laws of physics in their simplest forms describe systems are in the Lagrangian approach. Because if you remember, let's say in dynamics, we consider a certain particle and we put sum of forces on this particle, let's say equals to ma. So we follow this particle. We follow these particles as it's go. Look, I'm really sorry, but just my mother needs something. Sorry, 1 minute. Sorry again. Okay. So as we said, we have a certain problem that the laws of physics mainly deal with systems in the Lagrangian approach because they consist on following a certain particle. But in fluid problems, it is impossible to keep the track of the system in many cases. This is why what we should do, we need to connect these two approaches, the Lagrangian and Eulerian one. And what we will do then will allow us to come up with the different conservation laws for fluid problems. From here, we will define what is called the Reynolds transport theorem. Okay, so this theorem will consider a moving system that is system flows through a certain control volume. And in this case, the moving system will transport extensive properties across the control volume surfaces. What do we mean by this? So as I told you, when we consider any control volume, We can have fluxes coming in and other getting out. So we need to come up with a certain technique that allow us to connect what is happening between what is inside this control volume and what is crossing it in and out. Okay. Now I will, to be able to understand well this, I will give you a 2D example that will illustrate for you how we use this theorem. Okay. Nadim, no, I cannot hear you, Nadim. I don't know why I can't hear you. So if you need anything, just type your question here. Okay, Nadim? Okay, so what is the idea now? What we will do, we will try to connect, as we said, what is happening in a system and what is happening in a control volume. Okay, so the idea is that we will demonstrate that the variation of a certain property of the system is equal to the variation of the property in the control volume plus the fluxes that are crossing in and out the control surface. Okay, so what we will do then, we will try to apply a certain 2D problem together to demonstrate this. Okay, so what is the objective of the Reynolds transport theorem? The objective of the Reynolds transport theorem, as we said, is to connect what is happening in the control volume and in the control system. Okay, this might be complex as a first insight, but now when we will take a small example, you will understand. So if you consider, for example, here, what is happening in this system. Okay, we have the following system, which is like a nozzle, okay, of varying cross section, and we want to find the relation between what is happening in the control volume and the system. What do we mean by this? So, as we said, the system is defined by a fixed mass. So if I look at a mass, okay, I should follow it. Yani, let's say you have certain number of particles that you are tracking. Okay, let's say these particles are limited by this geometry. So you have these particles will go, one part of them is already inside your control volume. Okay, and one part will go are outside. So what will happen with time? This part will move, the particles that were outside of the control volume will get in it. On the other hand, another part of particles which was inside the control system, control volume, will go outside of it. Okay, I will repeat. So what we have here, we are exploring certain particles that are moving. These particles are getting inside, moving through this control volume, and then going outside of it. So at a certain instant, I will consider a certain part of particle. Okay, so I will consider a certain system. The system of particles here is limited by the blue line. You see the blue line? So these are the particles I am tracking. At this instant, you have two instants where you are exploring your system, instant 1 and instant 2. Okay? At instant 1, you just have this part of particles outside of the control volume, and the other part is inside the control volume. Now, what will happen? What will happen is that after a certain time delta t, this part of particles will get in the control volume, while part 2 will go outside. Okay? And what we want to do, we want to try to relate the control volume to the control system. Okay? So This is the approach that will be done. First, we will consider that, as we said, so a simple version of Reynolds transport theorem will relate system concepts to control volume concepts. And this is by doing the following case. First, we consider a one-dimensional flow through a fixed control volume, such as the variable area duct that is shown in this figure. Okay? We will consider first the control volume to be fixed. It's not moving. Okay? And this control volume is defined between these two sections. So, for example, if you look at this figure, this is my control volume of interest. It's limited by these sections. This is section 1. This is section 1. And this is section 2. Okay? And then I will consider the flow of mass that is coming in and getting out. Okay? So my control volume here is fixed. It's not moving while my system of particles is moving. So this is one of the possibilities. So now the system that we will consider is the fluid occupying the control volume at some initial time t. Okay? And after a certain time t plus delta t, the system will move a small position. So we mean by this, at a certain time t, we are looking at the system of particles that are in this position here. Okay? So what can we say then in this position? We can say that the control system can be defined here as this part. Okay, we have a certain part inside the control volume. We have a part that is trying to enter the control volume and a part that is getting out from the control volume. Okay, so imagine that the control system moves slightly to the right. So all the particles that will be coincident with section 2, the particles that are at this level, will move a certain distance, delta L2, equals to the velocity of particle at this section times delta t. Okay? While the particles that were entering the system in this time will move the following distance. They will move delta 1 equal to the velocity of particles at this cross section times delta t. Okay? And now what we will try to do, we will try to connect the expressions of system and control volume with time. So at the initial time, at time t1, when we started, okay, the system was just, if you want, equal to the control volume. Because what happened is that at the initial time, okay, we had all what was inside the control volume was considered as our system. Okay, so you are observing these two sections here, these two parts. Initially, you have a certain fluid that is inside this control volume. I consider that the mass, these particles that were at the initial state in the control volume are my system of interest. And now, as time will proceed, I will follow these particles. So what will happen with these particles? These particles will move forward, okay? They will occupy a new position. They will be, so after a certain time delta t, the particles that were here will move a certain distance, and they will be in a new position. And also particles that were at section 2 will move forward and will occupy a new position there. So now, after a small step of time, the control volume and the control system will be different, will not remain the same, but I can find a relation between them. Why? Because at the initial state, okay, this was the position of my particles, and this was my control volume. The control volume will not change, will remain in its place, while particles will move. As particles move, the control system will take a new position. So if you want, this is the new position of the control system. Okay? And if I take a small look, I can relate the control volume to the control system. How? Because now the control volume is the control system is the old part, okay, old part minus this one and plus this one. Why? Because particles moved a certain distance. They will not occupy the space anymore. And since I'm working with a control system, I follow particles. Okay, I follow particles. So here, this part now is not anymore a part of the control system since particles move. And a new part will be now a part of the control system, which is this one. So my new position of the control system is this one. So I can say now that my control system is this part plus this one, okay? And this part here is nothing than the control volume, which will not change in this problem. This part is the control volume minus part one. So I can write that after a certain time delta t, the system is equal to the control volume, which will remain the same in both scenarios, minus part one plus part two. Okay? So I can consider if I do a small physical interpretation, then what is happening is that the system is what is happening on the control volume minus what is coming in plus what is getting out. Okay? So now, if we consider if we want to write physically this, okay, what we will do? We will say we are exploring a certain parameter, any parameter. It could be the mass, it could be the momentum, it could be the energy of the system. So if I want to look at any property of the system B, okay, then I can say at the initial time before, I started by considering everything in the control volume as my system. So at the initial time, the property of the system is exactly equal to the property of the control volume. Okay. Now, since the system and the fluid within the control volume are coincident at this time, we can start with this condition. But after a certain time delta t, this will not be true anymore. Okay, why? Because this was my control volume, and the particles inside it were considered as my control system. After a small time step, the control volume will remain at its place, while if I follow the particles, one part of them will get out, and so here, and these particles here will move to this location. So now my system is in this position, okay, is in a new position. This is why I can write the following relation, that the property of the system at a time t plus delta t will be equal to the property of the control volume at t plus delta t minus b1, which is due to the part to this part, which is due to the particles that will come in and replace the previous particles, and plus the part which will go out. Okay. And now, since I am interested in the rate of variation of the property with time, so I can say I want to relate how the variation of property with the system is related to the variation of the property in the control volume. To do this, I will say that the variation of property of the system with time is the property of the system at t plus delta t minus the property of the system at t over delta t equals to, now I will just replace the property as the system at t plus delta t by its expression from here, which is the property of the control volume at t plus delta t minus b1 at t plus delta t and plus b2 at t plus delta t. Okay, and now since I know that b system at t is equal to the property of the control volume at the initial time t, I can replace this part by b of the control volume at t. So I can replace this parameter by b control volume at time t. Okay. So now all I have to do then is to consider the following equation. And as we expected, this is the Reynolds transport theorem. And what does the transport theorem tell me? It will tell me that the variation of the property in a system is equal to the variation of the property in the control volume minus, this is the inward flux, so minus the inward flux and plus the outward flux. So why the Reynolds transport theorem is like a connection between Lagrangian and Eulerian approach? Because when you talk about a control mass and you follow it, this is Eulerian approach. When you take a certain control volume and you look just what is entering and exiting it, this is Eulerian approach. So now this Reynolds transport theorem allowed you to correlate these two strategies. So it will help you a lot in solving fluid problems, because you can connect the variation of what is happening in a certain control volume with the variation of what is happening in the control system. You will understand much better this theorem when we apply it. We will do a lot of application on it. We will apply it on mass. We will apply it on momentum. We will apply it on energy. Okay, and you will get then the conservation of mass. You will get the momentum equation, which is equivalent to the second law of Newton for a fluid. You will obtain the energy equation for a fluid. All of these equations will be based on the following theory. Okay. So now, if we just look at our terms, we will see how to do the interpretation of the terms of that is coming in and getting out. Okay. So as we said, for the first term, which is when we consider, we will consider a very small time delta t. So the first term, as we said, b control volume at t plus delta t minus b control volume over delta t. This represents the variation of any property b, okay, within the control volume. And b, as we'll see, can vary, can be any property of the fluid. And in general, any property is specified per unit mass. Okay, so you can write that big B can be written as m, which is the mass, times small b. Okay, so we define always properties per unit mass, small b, and then for the control volume, when I want to see the variation of a property with the control volume, I can do, in case I have variation of the property over the control volume, I can do an integral approach. Okay, so I can say if at each point of the control volume I have different variation in B, be able to find the total variation, I should integrate over the control volume. This is why I can replace the property big B of the control volume by integral small b dm, and you know that the elementary mass dm can be replaced by rho dv. Okay, so then we can see here that this term, the first term of our Reynolds transport theorem, can be replaced by del integral over the control volume of rho b dv over delta t. Okay, now concerning the other terms which are concerned with what is coming in and what is getting out. Okay, so first we have b2 is the mass that is going out. Okay, how we can define the mass that is going out? So we can write it as the property B at section 2, okay, times the mass that is leaving section 2, okay? And the mass that is leaving section 2 can be calculated in which way? Because look what is happening. You are considering a certain boundary, okay? Particles will leave this boundary at a certain velocity. If you want to know what is the amount of particles that left your system, you can simply say that this is equivalent to the following. I have the cross-sectional area, I know it. At section 2, I know the cross-sectional area. Let's say it's area 2, okay? And my particles are leaving at velocity v2. And since I am considering a very small time step delta t, okay, then the length that is going out, if you want, the thickness that is going outside is equivalent to v2 times delta t, okay? So this thickness, I will call it, this thickness is delta L2. And when I multiply delta L2 by the cross-sectional area, A2, I can get the volume getting out, okay? So V2 times A2 times delta T, this is volume, the volume that is getting out, okay? And then I multiply it by rho to get the mass that is going out, and by small b, because each property, big B, is defined as small b, which is the property per unit mass, times the mass. So now, if you look at my expression, what I am interested in is the term B over delta T. So I will divide this term by delta T. When I divide by delta T will cancel out. And I will get the following, that this is a rate that is going out, rate of the property that is going out of my control volume, okay? And it's equal to, if I look at my terms here, it's rho AV times B. Rho AV represent what? It is m dot. It is a mass flow rate. Its unit is in kilogram per second. Okay. So as you can see here, B dot, big B dot out is m dot, which is the rate that is of mass going outside of my control volume, times the property small b. Okay. So in this way, we can say that the second term, which is B2 over delta T, represent a flow rate, okay, a flow rate of the property that is getting outside of the system. Similarly, for the inlet, I can do the same demonstration to say that B1 at T plus delta T over delta T, when limit delta T tends to 0, is equivalent to m dot n times B1. Okay. So all what I did here is just to demonstrate the following. Okay. It's just to say that if I go back to this formula, okay, I want to demonstrate that the variation of the property of a system is equal to the variation of the property within the control volume plus the fluxes that is getting in and out of the surface. This term, now we will see how we can demonstrate. Okay, so we have seen that B1 and B2 are related to the rate of mass going in and out. So we can demonstrate that these terms can be replaced by the following: integral over the control surface of rho B V dot N dA. Okay, let us do some analysis of this term. Rho is the density. We do it to transform from mass to volume, because dm will be replaced by rho dv. Okay, and dv we'll see that in the case of in our case, when we have a rate in and out, okay, when we divide it by delta t, because here we have a velocity term. Okay, this velocity term times dA will replace dv by dt, because here we have a rate. So dm by dt is rho dv by dt. And derivative of volume with respect to time will be equal to the velocity times the area. We will this is our purpose, to demonstrate now this term. We have already seen together now that we can replace this term. Okay, this is what minus b1 t plus delta t over delta t. This is minus rho, okay, times the property small b times a1 v1, where v1 represents the velocity. And this term is plus, so this is rho at section 1 and b at section 1. And this term is plus rho at section 2 times b at section 2 times area 2 and velocity v2. Okay, so if you look at these expressions, you can see that I am multiplying the area by the velocity. Okay, now if I want to, but for the outlet I have a plus sign, and for the inlet I have a negative sign. So if I want to come up with a general formulation that will work for both outlets and inlets, okay, I can use the following. If you have any surface, okay, any surface delta A, you know that you can define a certain vector that is normal to the surface. So normal to delta A. And the velocity that is coming in or getting out of the surface can be or along un, the vector, the normal vector n, or it can be with a certain, doing a certain angle with n. So not always the velocity that is coming in or getting out will be perpendicular to your surface. This is why, to come up with a general expression, what you will do is you will say that what I care for is the component that is along un. So it's the component that is of v projected on un. Okay, and we know that what can give us the projection is the dot product, because if I do v dot n, okay, v dot n will give me the magnitude of v times the magnitude of n, which is 1, times cosine of the angle theta between the velocity and the normal. Okay, so, and as you know, for cosine theta between 0, for theta between 0 and 90, cosine theta is positive, and for theta between 90 and 180, cosine theta is negative. What do we mean if theta is between 0 and 90? If theta is between 0 and 90, it's an inlet or outlet? Look, here, for any theta, this is theta 0, and this is theta 90. For any theta between 0 and 90, this is an outlet. And in this case, the projection of velocity vector on n vector is positive. On the other hand, if you consider theta between 90 and 180, okay, then what will happen is that you will have an inlet. So if your velocity vector is like this, okay, for any value between 90 and 180, then your flow will cross the surface towards the control volume. Then this is an inlet. Okay, this is why we say that just by putting v dot n will give you always the result, and it's a general formula for an inlet and an outlet, because for an inlet v dot n is negative, and for an outlet, V dot N is positive. So V dot N positive for an outlet, positive for outlets, okay, and negative for inlets. And this is what I want, okay, because in my formula we have demonstrated that everything getting out is counted as plus, everything entering is counted as minus. So by doing V dot N can replace for us the term plus V or minus V, because it will directly give us the appropriate sign. Okay, this is why I can say that for any general case, I can say that B out minus B in, because as we said, for everything that is going out is accounted as positive. Everything that is coming in will be accounted as negative. And V dot N automatically give me this side. It will give me a positive result for an outlet, a negative result for an inlet. So I can combine these two terms, which are some of rates that are of properties that is coming out, going out, minus rates that are coming in, equals to integral over the control surface of rho B times V dot N. Okay, V dot N dA. I know that this might seem a little bit hard, but you will see that when you apply this theorem, you will understand it better. Okay, so now this is the general Reynolds transport theorem. Okay, and we will see how to apply it on different scenarios. Now, we have also another problem that might encounter us, which is the following. So what if until now we have considered fixed control volume? The control volume is fixed and the control system is moving. We have mass that is coming in and getting out of the control volume. But what if both are moving, the system and the control volume? What can we do? It's not, we can do something to take into account this. All we have to consider is the relative velocity of motion between the control system and the control volume. Okay, because look, imagine that you have a certain pipe and you want to get water inside the pipe. If the water is fixed, if you just give a certain velocity for water, whatever is this velocity, the water will enter and exit your pipe. Okay. On the other hand, if your pipe is moving, to be able